Throughout the history of artificial intelligence, there have been two major paradigms for how AI might work, what we might call the symbolic and the neural paradigm, sometimes also called the computationalist or the connectionist. In this lecture, I'll explain the basic difference between these two paradigms and some of the important features and milestones of each. Before going into the details of symbolic and neural artificial intelligence, I'll describe a parallel distinction in the human mind. Cognitive scientists who study the mind sometimes say that there are two major types of thinking, what the Nobel Prize winner Daniel Kahneman calls thinking fast and slow, or less helpfully, System 1 and System 2. System 1, or fast thinking, is fast, automatic, frequent, emotional, stereotypical, unconscious. It represents anything that your mind does quickly and automatically, and usually has the feature that you can't explain how it works. You can recognize the face of a friend. You can stay balanced while pedaling on a bicycle. You yell when you stub your toe. You can create a grammatical sentence in your native language in answer to a simple question. But you probably can't explain how you do any of those things. System 2, or the slow thinking, is slow, effortful, infrequent, logical, calculating, and conscious. It represents anything where you know a sequence of rules to follow, and you can explain what you are doing in words, but you have to think to do it. You can multiply three-digit numbers. You can figure out which chess move is best. You can complete a checklist for filing your taxes. You can translate a sentence from your native language into a grammatical sentence of a foreign language that you've just started studying. In these cases, it's hard to do it, but you can explain how you're doing it. Historically, people have tended to think of these System 2 processes, or the slow, methodical thinking, as the domain of intelligence. But one of the recurring features in the history of computation is the discovery that the System 1 processes, these fast, instinctive thinking, has turned out to require far more computational power and ingenuity in order to program into a machine. One of the ways that cognitive scientists now think of this is that the fast processes of System 1 are a set of difficult abilities that we developed specialized instincts for through evolution that are wired into our brain, literally, while the slow processes of System 2 are the result of a single universal mechanism that could, in theory, do everything perfectly if we had sufficient time and detailed enough instructions. System 1 abilities develop through trial and error and play and practice, while System 2 abilities develop through explicit schooling and instruction. These System 2 processes of slow thinking are what we do when we pay attention to our thinking. Thus, these are the first processes that were developed into machines. Because this works with words and numbers, which are symbols that stand for things, we call this symbolic reasoning. During the 19th century, symbolic reasoning started fairly early. Inventors figured out how to use punched cards to give instructions to machines. This idea was developed in 1804 by Joseph Jacquard, a French inventor who figured out how to control patterns of colored thread in a weaving machine by means of these punched cards. In later decades, these punched cards were able to be used with automated clocks to let a worker punch their card to say what time they arrived and left. And voters could punch cards to indicate their vote. And with both of these things, machines could very quickly tabulate these punched cards to process large amounts of information quickly. One of Alan Turing's big breakthroughs in 1936, when he invented the general idea of symbolic computation, was in realizing that these punched cards could, in theory, be made to implement any algorithm whatsoever. Any algorithm could be translated into machine code if you could just break it down step by step at an even more basic level than you tell a student how to do it. You have to say, move the punch over one, punch it, move it back, do whatever it is. And if you can break down your complex process into that level of steps, you can program a computer to do it. One of the early programmers punching these cards for the Navy was Grace Hopper. And in one of her early programs, when she was punching cards and feeding them into a machine with vacuum tubes, she discovered a bug in her code. And literally, it was a bug, an actual bug had climbed into the machine. And she was realizing that with that sort of problem coming up when you had to manipulate the punched cards physically, she figured out a way to save later programmers the trouble of punching these cards themselves. She invented a program that would take words written in a language and automatically convert them into punched cards that told the computer how to follow those instructions. This was the first compiler for a programming language, COBOL. And when my mother was studying computer science in the 1960s, she was still compiling COBOL into punched cards for her work. And this is a big strength of symbolic reasoning, that once someone has figured out how to explain a process to a computer, you can tell another computer how to use that process in a bigger program. So we can give a name or a symbol to the one process and make use of it in a higher level process. Programmers call these frequent operations routines, and they call the earlier routine a subroutine when they use it in higher level work. So here might be an example of how you could use adding as a subroutine in defining multiplying. Each level can be fully explained and understood as long as you trust that the lower level works as described. We don't have to know how the add algorithm works in order to use it to define the multiply algorithm. You can design any algorithm you want as long as you can put it into words and someone else has come up with algorithms that already implement all those earlier words. And one interesting thing is that these algorithms can have loops. Not only can one algorithm call another one, but sometimes an algorithm can call itself. So think about what you're doing when you try to figure out what's the best move in tic-tac-toe. What you do probably is that you imagine doing any of the moves that you could do, and then you think, well, what would my opponent do if I did this? And then what you're doing is you're asking, what would be the best move in that situation? In order to find the best move in this situation, I have to consider every move, think what would be the best move in that situation, and to do that, I have to consider every move they might do and think what would be my best move. Because tic-tac-toe has only 9 moves, a computer can execute this full loop and play the game perfectly. But for bigger games like chess and especially for Go, these loops get quickly beyond the capacity of even the most powerful computers that we have today. So programmers don't always use this kind of self-recursive programming, but instead have to think, when do you tell it to stop and give it, and what instructions do you give it then? So while symbolic processing tries to mimic our explicit mental activity with words and numbers, the other kind of AI tries to mimic the biology of our body that gives rise to our instincts. By the early 20th century, neuroscientists had figured out that the brain was mostly made out of neurons, and that neurons are connected to each other in various ways. And a useful way to understand these neural connections was to think each neuron has a certain weight with which it's connected to each other neuron, and they will send an electrical signal to the ones that they're connected to if they get incoming signals that add up with their weights to more than the innate bias of the neuron. In 1943, Warren McCullough and Walter Pitts showed that a network of these neurons, with certain input weights from other neurons and certain biases towards or against firing, could give rise to a lot of interesting complex patterns. They didn't know if this was exactly how the brain worked, but it seems similar enough, and they figured the brain knows how to be intelligent, so maybe we could design intelligence out of these things. And one of the things they discovered is that if you just build some very simple rules for how the weights of these neurons change, like for instance, if you say neurons that fire at the same time start getting connected to each other, then they could start duplicating some of the simple reinforcement learning that psychologists like Ivan Pavlov and B.F. Skinner had been finding in animals in the early 20th century. There was a major advance with these neural nets in 1959 when Frank Rosenblatt made a device that he called the perceptron, which was built out of these neurons, and he could use this to classify an image. The idea was that he would hook up one input neuron to each pixel of the image, and then he would adjust the weights and biases of the other neurons appropriately so that we could get the output neurons to fire when something in particular is going on there. So in this example, these weights of -1, 0, and 1 are useful for figuring out if there's an edge in the image. You can see that if there's a lot of high numbers on the right side and low numbers on the left side, then you get a very high answer when you multiply these things together and add them up. Whereas if you're in a place that doesn't have a vertical edge, this isn't going to give you a strong signal. And at first, Rosenblatt would do this by adjusting these weights and biases by hand. But he eventually realized that if you had enough training images, you could just tweak the weights and biases automatically to classify the images correctly. And no one had to figure out those weights and biases or even understand them in order to give the right answer. The neural net would just work. In discussions of modern systems based on neural nets like ChatGPT, you sometimes hear people talking about learning these trained model weights. And this is what they mean. There's no code, there's no explicit instructions, there's just these weights and biases on the neurons. And we can't understand how it works, but that is everything about how the neural net works. By the late 1960s, when these neural nets were starting to be used for a few more applications, many symbolic programmers argued against them. Marvin Minsky showed that there were certain kinds of patterns that couldn't be learned with a network with two layers of neurons, no matter how many neurons there were, and that no one knew how to train networks with three or more neurons. Because a neural net just has weights and biases and no instructions and words, it's usually not possible to understand what it's doing. And so in the 1970s, work on neural nets stagnated, both because of this lack of understandability and because of the difficulty of training them. But in the 1980s, researchers like David Rumelhart at UC San Diego and Geoffrey Hinton at University of Toronto and Jan LeCun at Bell Labs started developing algorithms that could take advantage of new computational power that was available in the 1980s, and they could train neural networks with three or more layers, in fact, many layers very often, which we now call deep learning for deep neural nets. They're not just three layers deep, they're many layers deep. By 1989, Jan LeCun had designed a neural net that the post office was able to use to recognize handwritten zip codes. And several decades later, in 2012, Geoff Hinton developed a very deep neural net that's able to classify tens of thousands of different types of images. And many modern neural net algorithms are based on that. Even though neural nets are hard to understand, this is a feature that they share with human System 1 thinking, the fast and intuitive kind. As computational power has increased and training data has increased, neural nets have become more and more powerful, and they're used for more and more kinds of problems, despite this lack of understandability. New advances in neural nets allowed the different parts of the visual field to learn from each other, and they allowed large language models to figure out which words to pay attention to when predicting the next word. And so now, many things are done with neural nets. Much of this history of artificial intelligence parallels human development. When you first study something like a language or first learn to play chess, you think symbolically in words about what it is that you're explicitly trying to do. But once you become an expert, these sorts of things often become automatic and you start working instinctively. Procedures often move from system 2 to system 1. An expert often can't explain why they're doing something. They just know that it's right. That's why often it's not best to learn from the absolute expert because they don't know how to explain what they're doing. Now, there are still many researchers who think that neural nets are at most a temporary advance in artificial intelligence. For one thing, neural nets can't do the kind of infinitely nested loops that symbolic computational programs, at least theoretically, can. The neural nets are inherently limited by the number of connections. There might be billions of connections, but it's still an explicit finite bound, which the computational symbolic program doesn't have. For another, the lack of explainability puts limits on what we might want the neural nets to be involved in doing. Just as we often want a court to explain why they came to the decision that they came to, we might want an AI system to be able to explain why it has made the classification that it does. And in fact, some jurisdictions, like the European Union, have put laws in place to require explainability for artificial intelligence. So some researchers are now convinced that the future will have to involve some sort of synthesis of the symbolic and the neural approaches to artificial intelligence. But at the moment, that synthesis has not been developed, and neural nets have been at the core of most of the biggest developments in the past few years of artificial intelligence.